Hello, thank you for joining us for this session, the overview of the commercial mechanical provisions of the 2019 Oregon Commercial Energy Code. I'm Connie Umfrist, Communications Manager here at New Buildings Institute. Before we begin, I have a couple of housekeeping things to tell you about. First, you are muted and we cannot hear you. This helps keep the background noise down so that everyone can better hear the speakers. I want to direct you to the dashboard that you should be able to see on the right-hand side of your screen. If you are having technical difficulties and cannot see the slides or hear our speakers, you can use the question pane in this dashboard to let us know, and we will help you as we go. If there is time at the end of the presentation, we will answer a few questions. Please ask questions in this question pane as they come up. If there is not time, you will receive a follow-up email answering your questions. You will receive a follow-up email tomorrow with links to the recording and slides for this session. Our speaker today is Sean Denniston, NBI Senior Project Manager. Sean's work at NBI includes analysis and review of data relative to commercial building energy performance and prediction, code and energy program effectiveness, and energy technologies. Sean uses his expertise for code analysis, tool development, and research. He also manages NBI's new construction program, which provides technical resources for new construction projects. Sean, over to you.
Thanks, Connie. Thank you everyone for joining us today as we talk about Oregon's new energy code and target in on the HVAC section. Really quick, want to introduce you to NBI. We are a nonprofit that work to continuously improve the energy efficiency of commercial, multifamily, and now even residential buildings. We work in a few different program areas: best practices in new and existing buildings, continuous code and policy innovation, and zero energy leadership and market development. Today, we would really like to thank the sponsors of this training session, the Northwest Energy Efficiency Alliance and the Energy Trust of Oregon with assistance from ClearResult. We also want to thank PNNL and the Department of Energy and the Oregon Department of Energy for providing additional content for this presentation and this training. A lot of this information is provided by them, and we're able to bring it to you tailored for Oregon specific application. I think it makes sense to start with a little bit of background about why the energy code in Oregon is changing and how it's advancing. We have goals in Oregon for improving the emissions profile of really everything in the state, but especially for construction. And this is based on legislation in Oregon that seeks to advance the energy codes. But we also have some more specific things. We have the Executive Order 1720, which mandated that the Oregon code be updated, in this case by October 1st, 2022, to exceed certain levels of efficiency. And those are based on the national model codes that we have from either ASHRAE or the IECC. And as a result, in Oregon, what the Oregon has decided to do is to move from what was in place before, which was kind of a specialty code that was a hybrid of some of the national model codes, but with a whole lot of local amendments that really made it special, something unique to Oregon. But the desire was to move to something that was a little bit more universal. And so Oregon has adopted ASHRAE standard 90.1 as the basis for its energy code, but not just simple ASHRAE 90.1. Oregon, in trying to reach these policy goals, has gone ahead and adopted what is a version of what is called the zero code. We might call it, in this case, a zero ready code. And what this is something that has been put out by Architecture 2030, and it's a framework for getting to zero energy. And it's based on ASHRAE 90.1 levels of efficiency from 2016, and then you add renewables. Now, the reason that in Oregon it's a zero ready code instead of just a zero code is that you don't actually have to install the renewables. You just have to provide the calculations for how much renewable energy it would take to get your design to zero energy once you design to ASHRAE 90.1. And Architecture 2030 has provided several tools to help you do that, including this, which is the the solar PV calculator. And this would be the simple way that one simple way that you could use to actually do the calculation, enter some basic information about your building and the type of renewable energy system that you might install on your building, and it would give you the information that you would need for your code submittals. Oregon, this is a submittal process, so you'll have to submit this along with your standard documentation that you would use as part of your code submission. Also want to point out that just recently, Oregon also decided to do a statewide alternative method based on IECC 2018. So we're going to be talking about ASHRAE today because that's the main basis for the code, but you could also do 2018, which is actually probably a little bit more similar to the code that was in place in Oregon before. Just to give you an overview of how ASHRAE 90.1 is structured, because it is structured differently than what Oregon has had in the past. We have your standard purpose and scope sections, definitions, administration, and enforcement. And then we have chapters that are dedicated. Chapter 5 for building envelopes, 6 for heating, ventilating, and air conditioning, 7 for service water heating, 8 for power, 9 for lighting, 10 other equipment. And then there's Chapter 11, which is the energy cost budget method. This is one of the modeling methods available in 90.1. And then a series of normative references and normative appendices, A through H. Now, there's a lot of things in the appendices. Probably the one you might be the most familiar with is Appendix A, which gives you the U factor and R values for various envelope assemblies. But one of the other really big ones of note, of course, is Appendix G, which is the second modeling methodology that is available in 90.1. Now, 90.1 applies only to certain buildings, so new buildings, portions of new buildings, new systems in buildings, so for alterations, new equipment in existing buildings. But one of the important things to remember, it does not apply to single family homes or low-rise multifamily. So in this way, it's very similar to the Oregon Commercial Code that was in place before. And of course, it doesn't apply to buildings that don't use any electricity or any fossil fuels. This is an energy code. It doesn't really make sense for it to apply to a building that doesn't really use energy. As you go through, like all codes, there's going to be certain exemptions that are in place that you're really only going to find through using the code. And of course, the standard proviso that we have in almost all energy codes, that no matter what the code requires, it's never going to make the building less safe, less healthy than the codes otherwise are going to require. So in 90.1, there's really 3 compliance paths. It's probably the easiest way to think about it. There's the prescriptive path, the energy cost budget that we talked about, Chapter 11, and Appendix G. Now, this is something new with Appendix G. Even though a lot of jurisdictions have allowed Appendix G to be used for code compliance, historically, that's not really what it was meant for. It was meant to be used as a rating methodology, but in 2016, it has been reworked specifically to work for code compliance. Now, since we're talking about HVAC today, we really want to focus in on how you would navigate through the HVAC section. This is, of course, the Chapter 6. There are a series of mandatory provisions, and then there's the prescriptive option, and then you can use these 2 modeling approaches. But there's also a simplified approach in ASHRAE for simpler buildings. So if you're going through, you have the general sections that you have to follow no matter what. 6.1 has some general things in it. 6.7 has submittals. 6.8, of course, is minimum equipment efficiency. No matter how you do it, you're going to need to comply with all those. But then you can follow a simplified approach, which is meant for simpler buildings. You can follow the mandatory provisions and the prescriptive path, so a prescriptive path through. You can do the mandatory provisions, and there's a special alternative compliance path for computer rooms, recognizing that they're separate, that they're a unique set of circumstances since you're conditioning for equipment rather than for people, or you can go through one of the modeling sections. Now, I want to point something out about Appendix G before we go much further. Appendix G, as I had mentioned, has been reworked in 2016. So that equation that you see at the top, which was kind of the historic way that it worked, you can see the proposed building performance over the baseline building performance, and you get a performance cost index. They've replaced that equation with a more complex equation, when we're looking at it, more complex methodology, but it has some real advantages to it. So if you are using Appendix G, we don't really have time to dig into this, but just recognize that Appendix G works differently now than it did before. There are some more tables, there are some more factors, the compliance equations are more complex than they were before. So make sure that you pay attention to that as you are going through. But today, we're actually going to use the simplified approach to guide our training. And the reason for this is that we really have way more content in the HVAC section of 90.1 than we can really cover in an hour. But the simplified approach, it applies to 80 to 90% of the buildings out there anyway. It's called the simplified approach because it's meant for simple equipment, which you generally find on smaller, some medium-sized buildings, or even some large buildings that are just very simple, like warehouses. So it applies to a lot of projects to start with, but it also gives us a pretty good overview of the types of requirements that we have in ASHRAE, and also gets us familiar with the structure of ASHRAE. So 6.3 is the simplified approach option. You can use it only for buildings with 1 or 2 stories. They have to be smaller than 25,000 square feet. They have to have a single HVAC zone. So that's one of the big things. And then there are a series of additional requirements. And really what these requirements all do is they map into the mandatory and prescriptive requirements that are in Chapter 6 and picks up the ones that are important for the, for simple HVAC designs. Throughout this presentation, you'll notice that some of the things are in red, and this denotes something that has changed in 2016 versus 2013. Even though ASHRAE wasn't the code in Oregon, many of you are probably familiar with ASHRAE and used it since it was an alternate compliance method in a lot of jurisdictions, or you've worked in other jurisdictions and you might be a little bit familiar with it. So let's really just dig right in and start with B. And that begins with fan control. And it has a series of requirements for air handling and fan coil unit supply fans. They have to be controlled by 2-speed motors or variable speed drives. And there are a series of additional requirements on direct expansion units and how this interacts with the economizer. You'll notice temperature control on the zones and the minimum fan speeds. And this really gets to how the fan is controlled in these systems. When you get into ASHRAE, the requirements are generally pretty straightforward. This is one of the places where you have a low speed and a high speed control requirements. So just keep in mind that you want to make sure that your fans fit in with this set of requirements. I think one of the really big things is the equipment efficiency. So in table 6.8.1, and there's a whole series of them, this is where you will find the equipment efficiencies for all HVAC equipment. ASHRAE has the federal minimum requirements in it. So just like every other jurisdiction, ASHRAE can't go above what is mandated as the federal minimums across the country. And so we have different classes of equipment, we have different sizes of equipment, some subcategories, and then minimum efficiencies. And different kinds of equipment are rated with different systems. So we have SEER, we have EAR, we have IEER, HPSF. So we have a whole bunch of different equipment ratings. And as you go through this, you'll be able to find the equipment is always, the efficiency rating is always prominently labeled on the equipment, and it should be pretty easy to find. This hasn't been updated in a few years, so this really should be nothing new for you. Now, economizers are one of the areas where there's a certain amount of complexity, and this is on that option D that we looked at earlier. And there are broad sets of requirements for when an economizer is required. And just from an overview standpoint, an economizer is a piece of equipment that attaches to the space conditioning equipment that brings in outdoor air. And the idea is that because a lot of commercial buildings are internal load dominated, that they need the conditioning those spaces. Sometimes they need cooling when the air outside is actually already cool. So you can bring in outdoor air instead of conditioning the air from the interior and recycling it. So it's sometimes called free cooling, although you still have your fan power. And the economizer brings it in. And there are a lot of situations where economizers are required. However, there are some trade-off options as well. Generally limited to unitary systems in this approach. If you don't want to do an economizer, then you have to raise the minimum cooling efficiency, and we'll talk about by how much in a moment. And there used to be a separate table for computer rooms. This is one of the things that we were talking about earlier. But now they follow the same threshold as other spaces because there is this specialized approach elsewhere in the code. So here is a table that tells you how the economizer needs to be controlled. This is an important thing because how the economizer is controlled, effective control varies from climate to climate. So we can see in the Oregon climate zones that there is when you can use a fixed dry bulb temperature, when you need a differential dry bulb temperature, fixed enthalpy or fixed dry bulb temperature controls are allowed in all climate zones. And you've got an equation and a description of how the economizer control works. So this is one of, I think, probably one of the more important tables that you're going to use because it's going to tell you how to control the economizer function. Now, I mentioned that if you want to just avoid using an economizer, because it does make the system more complex, you can just put in more efficient cooling equipment as an alternative. This is something that makes it simpler, and since the equipment requirements that are in the federal standards are actually a little bit low. They haven't advanced with the market. There is much more efficient equipment out there on the market. So if you want to avoid the economizer requirements in Oregon, then you're looking at a 64 or 59% higher cooling efficiency rating on your equipment. So this is to make up for the fact that you're not using that outdoor air as your quote unquote free cooling. On F, there is also a requirement for exhaust air energy recovery. So this is when you recover the conditioning energy from your exhaust air into your in-air stream. It's only required in certain conditions. So one of the big things is supply air capacity. So it's only required on somewhat larger equipment. And we have a set of tables that tell you when it's required. And those values are based both on climate zones. So we'll have values for our 2 climate zones, but they're also based on the percent of outdoor airflow rate. So some buildings require more outdoor air than others. The higher the outdoor air rate, the more likely you are to need energy recovery. This makes a lot of sense when you think the more air turnover you're getting, the more energy you'll be losing from replacing that air. There are a couple of additional tables for looking at different size ventilation systems and how the energy recovery applies. So we have one table for systems operating less than 8,000 hours a year, and then another table for systems operating more than 8,000 hours a year. Again, getting at this, the more outdoor air that you're using, the more you are justified by using the energy recovery ventilation system. And you can see those here. So for our climate zone, and that's actually just one of our climate zones. You should be also looking at the top one there. You can see in a lot of cases in 4C, so out on the coast, it's not going to be required at all for ventilation systems that run less than 8,000 hours a year. For systems that are running less than 8,000, we will see it in our other climate zone, but only once we get up to those larger sizes. And then if we look at the ventilation where we're looking at more than 8,000 hours per year, then 4C will begin to have requirements, not at the lowest levels of outdoor air, but it kicks in pretty quickly. And then we have it across the board for our other climate zone. And this is the requirements for energy recovery is that you have to have a system effectiveness of greater than 50%. This is something that's different than we've had before. We want to make sure that this works for smaller energy recovery products because the thresholds for when energy recovery have also been lowered. And then we've also got some additional definitions that have been added to help with some of the requirements that are in place. So an enthalpy recovery ratio is the change in the enthalpy of the outdoor air supply divided by the difference between the outdoor air and the entering exhaust air. So this is a percentage. And then sensible, and it's the change in the dry bulb temperature of the outdoor air supply divided by the difference between the outdoor air and the entering exhaust air. So one of the things you'll see here is enthalpy and sensible. So we're looking at sensible versus latent energy recovery. There are, of course, a whole bunch of exceptions to this. And a lot of these, make sense. Lab systems, certain lab systems, not all of them. Systems serving uncooled spaces, so spaces that don't have a lot of space conditioning. When more than 60% of the outdoor heating is provided by site recovered or site solar energy, so you're not going to get much benefit out of energy recovery. When you have cooling energy recovery in 4C, that's going to be applicable here. Certain requirements around airflow. When you have systems that require dehumidification, that employ energy recovery in series with a cooling coil, and of course, systems that just don't operate a lot, so less than 20 hours a week at outdoor air percentages as in the table. So make sure that you're checking all of these exceptions, and because some of your designs won't need to have the energy recovery, even if you do qualify for the thresholds in those tables, because the code does carve out some of specific applications. Now, we're gonna cover the next couple of criteria in the simplified, pretty quickly. Oh, sorry about that. So there's a simple requirement for thermostats that it has to have a manual changeover or dual set point thermostat, which is not a very high bar for thermostats. In simple systems, of course, more complex systems are going to have a separate set of requirements, including deadband control. In the simplified approach, there's a heat pump supplementary heat lockout. And what this is when you have a heat pump providing heating, then you need to have the equipment needs to lock out the resistance backup heat when the heat really can be provided adequately by the heat pump. Some systems under normal operation will actually be designed to use the electric resistance heat to heat up more quickly, to do a rapid heat up. So this prevents the system from doing that if it's possible for the heat pump to do it, even if it's a little bit slower. There's prohibitions around reheat or simultaneous heating and cooling for humidity control. This is something that we see in a lot of systems where they'll cool the air and then reheat it. So that would be prohibited. And then there's some time clock controls for the equipment that apply broadly to equipment, except for hotel, motel, guest rooms, and systems requiring continuous operation, and we're actually going to talk about that right away. So one of the things that might be new to a lot of people is the hotel motel controls. This is something I'm sure a lot of you have experienced. You check into a hotel and you get in there and it's, the thermostat's been at 60 degrees for the last, 3 years because it's always that way whether or not there's anyone in there. So ASHRAE has requirements for controls for the HVAC system to actually bring down the HVAC system when the rooms are unoccupied. So there are a series of requirements. One, when the the room is unoccupied. So within 30 minutes of the guest leaving, it needs to automatically raise or lower the set point by 4 degrees, depending on whether we're in heating and cooling. Not a big difference, so this isn't something that's going to have you coming back to an uncomfortable room, but enough to make a difference in the energy consumption. Now, for a room that's unrented and unoccupied, then the set points automatically reset to 80 degrees or higher for cooling and 60 degrees or lower for heating. So this is a room that no guest is expected, no one is going to be checking in, it's just unrented and there's no one in it. So we're going to allow it to go farther out of what might be considered the typical comfort range. And then it has a couple of conditions for when a room would be considered unrented and unoccupied. So either continuous unoccupied for up to 16 hours, or you could use networked guest room control systems that indicate that the room is unrented and occupied for 30 minutes. This is a lot of hotels now have a unified system that magnetizes your card and it can all work together. So you can use either of these approaches, but it also applies to ventilation. So within 30 minutes of all occupants leaving the guest room, the ventilation and exhaust fans should also be turned off or use isolation devices to do so. But this doesn't prevent outdoor air purges. And this is a key element of making sure that the room doesn't get musty and stale. So even though you might be bringing down the ventilation level because no one's in there, no one needs fresh air, you can still do a purge cycle on the room to keep the air generally fresh, to keep the room generally fresh. And like I said, captive keycard systems can be used to comply with the set point and ventilation requirements. You will see in some jurisdictions, this is pointed out specifically because in some jurisdictions, you're not allowed to use these simple controls. You have to use more sophisticated hotel room controls for determining occupancy. But under ASHRAE, you can use captive key card systems, which are a pretty straightforward system to work and integrate in with a lot of hotel systems. Keep in mind, this is only for 50 rooms or more. So if you have your little boutique hotel or a bed and breakfast, this isn't going to apply to those. This is really looking at your larger establishments. Now, one of the big things, of course, is the insulation on piping that is used as part of the refrigeration system. This is L, and we have a whole set of requirements for minimum efficiency. And these requirements vary based on fluid operating temperature. So as the temperature gets higher, of course, the insulation requirements get higher. And then there's specific requirements for the insulation. So a minimum insulating performance for the insulation, and then a minimum thickness at that performance. And that varies by the size of the pipe as well. So you see varying by the temperature of the fluid in the pipe, and then a varying by the thickness, by the size of the pipe. And this is something that's going to apply, anytime that you're using fluid to distribute heat and energy throughout your building. There are, as all things, there are some exceptions to the requirements in this table. If you have factory installed insulation, if you have piping that's conveying certain kinds of fluids, so for operating temperature range between 60 and 105 degrees, so these are not especially hot pipes, so those are exempt from those insulation requirements. And any that haven't been heated or cooled through the use of fossil fuels or electricity. So in this case, you're probably looking at, this is mostly going to be solar thermal pipes, but this is something that might apply to some of the piping that is part of a ground source heat pump system. If you can demonstrate that heat gain or loss won't increase the energy use, that puts the onus on the building designer to demonstrate that. And then for any piping less than 1 inch, no insulation is required in certain circumstances like strainers, control valves, and balancing valves. Those things that can be really difficult to insulate. So if you're already not requiring a lot of insulation in that application, on these areas where it's difficult to apply the insulation, then it's not required. So on criteria M, we have requirements for duct insulation. And these are minimum requirements for the amount of insulation that needs to be on the ductwork. And this comes to a table again. So like the piping, we have certain climate zones, and then we have certain pipe sizes, and then we have different duct locations. So whether it's an exterior duct, which are limited, you can only use exterior ducts in certain circumstances. It's a bad practice. Hopefully no one's using them at all. When they're in an unconditioned space or they are buried ducts used to be a fairly common practice, a little bit less common now, but you might still see them. And then in indirectly conditioned spaces. And we also have different requirements if it's for heating only or cooling only. So we've got this set of conditions that we can look at for when pipe insulation and how much duct insulation is required. And there are also requirements for duct sealing. Now there's a general prescriptive requirement that ductwork and plenums with pressure class ratings should be constructed to seal class A. This is generally mechanical fasteners, mastic, that sort of thing. And so it's a very prescriptive approach. This is something that should be very common. However, any ductwork that is over 3 inches of water gauge static pressure, so these are ducts that you would consider high pressure ducts, have to be leak tested. And luckily you don't have to do the whole thing. It's a 25% representative sample, but they have to be leak tested to 4 CFM per square foot. Now this is an increase in ASHRAE 2016 over 2013 and could represent for some projects, some people who are used to Oregon, a real performance improvement there. But the 4 CFM per square foot is very attainable. So we have a series of additional, the next set of criteria, just give you a little preview of what we're going to be looking at, because as we get toward the end, they're starting to get a little bit simpler. So one of the requirements is for duct balancing. This is a pretty basic requirement that you have, as you have your branch system going out, that the ductwork needs to be balanced to deliver the right level of air to each one. And this is really just a documentation requirement, since this is something that needs to be, is something that's done in the field. So your documents have to show how the duct balancing should be done. There are a series of requirements for outdoor air control, and this includes different circumstances and different applications. And so we see 4 main ones here. So for stair and shaft vents, they have to be equipped with motorized dampers that are capable and configured to automatically close during normal building operation and are interlocked to open as required by fire and smoke detection systems. So, these are the sorts of vents we want to make sure that we have an interconnection between space conditioning and emergency operation. Then we have shut-off damper controls. So all dampers for outdoor air, both intake and exhaust, need to be equipped with motorized dampers that will automatically shut when the system or spaces are not in use. So, this is a lot of systems have used either barometric or just gravity dampers. So in this case, they need to be motorized to really close off those dampers when they are not in use. Sorry about that. And of course, there are exceptions to that. Gravity dampers are acceptable in shorter buildings, for example, and relief dampers in buildings in certain climate zones and backdraft dampers. So make sure you take a look, because there are going to be a few exceptions. You're not going to have to use motorized in all circumstances. So ventilation systems that are serving unconditioned spaces, which makes a lot of sense. And then of course, kitchen exhaust hoods, because of the contaminations that come out of those dampers that can lead to failure. However, there are requirements for damper leakage. In this case, there's a whole section on it, 64341, One of the things about ASHRAE, you'll notice the numbers get pretty deep pretty quickly, and that has a maximum leakage rate in that table, and when tested in accordance with one of the AMCA standards. And then there are ventilation fan controls, and highlighted this one a little bit more specifically. So if you have a ventilation fan motor greater than 0.75 horsepower, you have to have automatic controls to turn off the fans when they're not required. So, basically when the ventilation system is not operating. The big exception to this, of course, is when you have fans that are intended to operate continuously. So if there's not a non-operating condition, then there's no need for the controls. There's also a requirement to prevent simultaneous heating and cooling. So this is a big deal when you have separate heating and cooling systems. It's very easy for them to get working crosswise and one to be heating while the other one is cooling. So if you have separate heating and cooling systems, then the thermostats have to be interlocked. So, and this is just either a communication protocol or an actual interlocking device between the thermostats that prevents simultaneous heating and cooling to avoid the situation here where you've got the systems right next to each other. And then there's also a requirement for optimum start. And so right now, the ASHRAE requirements just require optimum start when you have supply air capacity greater than 10,000 CFM. And what optimum start does is it gets the equipment really, well, going ahead of time. So I think the definition is probably the easiest way to think about it. Controls that are designed to automatically adjust the start time of an HVAC system each day with the intention of bringing the space to desired occupied temperature levels immediately before its scheduled occupancy. So if it takes 15 minutes for the system to bring the occupied space up to temperature, then the system will come on 15 minutes ahead of time. If it's 30 minutes, then it'll come on 30 minutes ahead of time. And the idea is to really make sure that you hit the right comfort temperature before that set point says that the equipment is supposed to, that the space is supposed to be at that set point. You might think, how does this save energy? The big thing is behavioral, actually, that if the space is at temperature when it's supposed to be, it makes it less likely that occupants will come in and say, ooh, it's cold in here and it's supposed to be warm. And so they'll over adjust the system and it'll actually be running high or too low during the occupancy period because they overcompensated with the thermostat. There are also requirements for demand control ventilation. Demand control ventilation, again, we can use the definition that's in the code to understand what it is. It's a ventilation system capability that provides for the automatic reduction of outdoor air intake below design rates when the actual occupancy of spaces served by the system is less than the design occupancy. So this is a control methodology that will bring the outdoor air down because you don't have people who actually need the fresh air. Of course, since every time you bring in outdoor air, that is energy loss because that's air that has to be conditioned. So anytime that you can turn down your ventilation rate safely, that's a good thing. It's only required in certain circumstances though. DCV is not required in all circumstances. So for zones that are greater than 500 square feet with a design capacity of greater than 25 people per 1,000 square feet, and where the HVAC system has an air size economizer, automatic modulating control of the outside air dampers, and design outdoor airflow of greater than 3,000 CFM. So what you're seeing here is both a system that is capable of modulating its outdoor air, but also is bringing in enough outdoor air where the investment in demand control ventilation equipment actually is justified by the amount of savings that it can generate. And as always, there are a whole lot of exceptions to demand control ventilation. We have certain systems with exhaust air energy recovery. So if you're already doing energy recovery, demand control ventilation is not going to be saving as much energy, so it may not pay back for itself. When you have multiple zone systems without direct digital control of the individual zones communicating with a central control panel. So you have multiple zones and basically you don't have a control system that's smart enough to control them all, the outdoor air separately. Systems with a design control airflow of less than 750 CFM, spaces where more than 75% of the outdoor air the energy is coming from other places. This should look familiar from our energy recovery. And then we have certain spaces defined per ASHRAE 62.1, and just in case you're not familiar, ASHRAE 62.1 is the ventilation standard for commercial buildings. So it defines airflow rates and outdoor air levels for different space types. And so there are certain types that do not have to have demand control ventilation: correctional cells, daycare, sick rooms, science labs, barber, beauty and nail salons, bowling alley seating. So, I mean, in a lot of these cases, you're looking at either security or you're looking at spaces that really do need the fresh air, maybe all the time, not just when there are people in there, because there are other contaminants. There's also a requirement for door switch controls. And so these are controls that will turn off the HVAC system basically when a door to the outdoors is open. And what it will do is it needs to be able to disable the heating or adjust the set point within 5 minutes, or disable the cooling or adjust the set point within 5 minutes. There are a series of exceptions. I think you can think of a lot of applications where you might see this, especially in the trend in restaurants to have roll-up doors on for their seating, so that you have these roll-up doors. That would apply in this circumstance. However, it doesn't apply to several situations. So any entries with automatic closing devices, so your automatic doors, of course that makes sense because it's going to close it automatically for you. Spaces with no thermostat, of course alterations to existing buildings, this is a difficult thing to retrofit. And then loading docks, since that's really a different class of space. So that's the simplified HVAC approach. And we've used that to take a high level look at the HVAC requirements in the code. Now, if you have a building that has a more complex HVAC system, a VAV system, one of these, or a larger building, a taller building, there are going to be more specific requirements and more sophisticated and complex requirements for those systems. So make sure that you look through the chapter 6 for the things that apply, and it really hits all levels of HVAC design. That's one of the things to keep in mind when you are using ASHRAE, since ASHRAE is the American Society of Heating, Refrigerating, and Cooling Engineers. There is a real focus on the mechanical engineering part, and so a real focus on getting a good set of requirements for the mechanical systems in the building. One of the things, though, that we need to talk about when we're talking about mechanical systems is also service hot water. And in chapter 7, we have all the requirements for service hot water, a set of mandatory and prescriptive requirements. Now, the first one, which is perhaps one of the most important, is just the insulation requirement. So there is a table that you have to meet, we'll look at in a section, in a second, that is minimum insulation levels for anytime you have circulating water heat. So, this is your recirculation loop, supply and return piping, anytime that there's something that's going to keep the hot water in the pipe most of the time. But there's also requirements for non-recirculating storage systems. So these are requirements for insulation that is near the storage tank, recognizing that we do have a certain amount of migration that goes out of them. And then anything that's externally heated pipes, direct heated pipes. So heat trace or impedance heating. So these are, they're being heated by an element that's actually on the pipes and not by just putting hot water into them. And this should look very familiar because this is the same table from the mechanical system requirements. You would be looking, while in the mechanical system, you might be looking at some of those higher temperature ranges. And for service hot water, you might be looking at the lower ones, but this should look familiar. It's the same table and the same basic approach, varying by temperature and then by pipe size. And you can see that as the pipe gets larger, you're going to need more insulation. And as the temperature goes up, you'll need more insulation. This is really going to be, we'll see this in a lot of circumstances, but probably the most critical one that we should be thinking about is high-rise multifamily. That's where this requirement is actually going to have a really big impact on energy usage. We also have a series of control requirements, and these are based around both pumping energy, but also the control of the temperature that's delivered. So 744 requires for temperature controls, temperature maintenance controls, outlet temperature controls, and circulating pump controls. So let's go ahead and look at that. So temperature controls shall be provided that allow for storage temperature adjustment from 120 or lower to a maximum temperature compatible with the intended use. The idea here is that we want to be able to adjust our storage temperature to actually meet the application that we're using. And that's going to change, especially when, depending on the distance that the water needs to travel to its point of use, to whether it's just being used for, say, bathroom versus feeding into a commercial dishwasher. Our temperature requirements are different for these different applications, so we want to make sure that our storage tanks are capable of delivering those different temperatures. There is an exception if the manufacturer's installation instructions specify a higher minimum thermostat setting for reasons like condensation or resulting corrosion. We'll see that in some circumstances, but that's something that'll be documented in the specific equipment documentation. We also have requirements for temperature maintenance controls. So systems designed to maintain usage temperatures and hot water pipes. So these are your recirculating hot water systems, including those with heat trace, shall be equipped with automatic time switches or other controls that can be switched to switch off the usage temperature maintenance system during extended periods when hot water is not required. Now, in a lot of commercial buildings, this will look like a recirculation pump that makes sure that you can get hot water out to all of your bathrooms, because maybe you've just got one water heater and you've got bathrooms in remote locations. You want to make sure that hot water gets to them before they're done washing their hands. And so in that case, the automatic time switch, it only runs when the building is active and it turns off at night. That's a pretty standard, straightforward approach. However, you can also use demand control in this circumstance. It doesn't have to be just automatic time switches. You can use demand control, which is going to be more efficient because it's only going to be running that pipe when you actually have demand. It'll really run that water out to the place quickly. The wait time for the hot water, though, in a demand control might be a little bit longer. Now, going to multifamily high-rise, that's where things look a little different. These control requirements are really made for that commercial setting. And in high-rise multifamily, you might want to see some more sophisticated recirculation controls that recognize that in multifamily, which is a residential occupancy, your demands for hot water may not follow a simple time switch schedule that is easy to set. People take showers in the middle of the night. And so you might need to think about the control strategy that you use in that circumstance. We also have requirements for controlling and limiting the temperature of water that is delivered at lavatory faucets. This is basically an anti-scalding requirement, but it's also, there's an energy efficiency element to this. 110 degrees is good water temperature for washing your hands, an upper limit that's actually fairly warm, fairly hot actually. And so want to be able to limit and make sure that you're not delivering too hot of water. And then we have a requirement for circulating pump controls. These are different than your recirculation loop. This is when you have water circulating from a storage tank to a boiler or another source of hot water, and it's meant to turn off the pump when you're not actually heating the water that's going to the tank. A lot of older systems, they would run with just a continuous pump, and it would be continuous pumping back to the boiler, and then the boiler would come on and it would heat up the water, but then when it would go off, the pump would just keep running. And so this changes that so that the pump only runs when the boiler is actually on, and then it has to shut off within 5 minutes of after the end of the heating cycle. And we do have some requirements for heat traps. So when you have a non-circulating system, you have to have a heat trap on both the inlet and the outlet of your storage tank. And this is really meant to just keep the hot water from migrating up into the pipe. That bend in the pipe does exactly what the name says. It traps the heat in there, since it's convective currents that are making that hot water move. And this is any time that you don't have integral heat traps, which a lot of your storage tanks will have, but not all of them, especially the smaller ones. And then we have a set of requirements for when the same equipment is going to be used for both heating your hot water and for heating your hot air for space conditioning. And you can do combined space and water heating when you meet one of these 3 criteria. If you have a single boiler or component that is heating the service water, has a standby heat loss not exceeding, and then we've got a calculation, so you're gonna have to do some math and based on your design to figure out when you can do that. Really what this intends is you have to limit the amount of standby losses in your equipment if you're going to use it for both. The jurisdiction agrees that the use of a single heat source will consume less energy than separate units. This is almost like putting into text an alternate means and methods. You need to establish to the building official that your single heat source is not going to consume more energy than separate units, which is the case in a lot of circumstances. Or when the energy input of the combined boiler and water heater system is under 150,000 BTUs per hour, which is not an especially large boiler. Right at that point, we're looking at, this is the class of boiler that you still might be seeing in some single family residences. Not all of them, it's a little bit big probably for a lot of single families, but so we're not, this is a fairly small boiler, but we have a lot of fairly small commercial buildings out there. And that covers the highlights of the water heating as well. Keep in mind that for both HVAC and water heating, if you take one of your modeled performance approaches, you are still going to have to meet the mandatory minimums, and we talked about some of those today, but you have the opportunity to do trade-offs. There aren't a lot of trade-off opportunities in water heating. Really, when it comes down to it, the requirements are pretty straightforward, and so there aren't a lot of trade-off opportunities. There really aren't a lot of trade-off opportunities within the HVAC system. A lot of those trade-off opportunities really come from doing more efficiency in your HVAC or your water heating system, mostly from equipment, and being able to trade that off against other systems. So it looks like we have about 5 minutes to maybe get a couple of questions in. And if you have a question and we don't have time to get to it, then we'll go ahead and answer that by email after the fact. So, Connie, do we have any questions?
I have 2 questions that have come in. I will start with this one. It's a little long, so bear with me.
Okay.
An exception to 90.1 2016, Article 4.2.1.3 exempts historically significant buildings that are being renovated from complying with the requirements of 90.1 2016. It does not indicate what a historical building would need to comply with in lieu of this standard.
So
what energy code requirements do historical buildings that are to be renovated in Oregon need to comply with?
So if you are following the ASHRAE path, then historic buildings are exempted. This has been the traditional approach for historic buildings, is just because of the complications that arise from having, the idea of trying to require changes to historic buildings from something like an energy code. If you go through IECC 2018, it has a somewhat different approach to historic buildings. It only exempts historic buildings from the provisions that would be damaging to the historic building. So you would still have to comply with everything else. Really, when it comes down to it, the only energy requirements that you would have to meet in historic buildings are those that are set on equipment by federal standards. So minimum requirements for equipment, when you put new equipment in, whatever minimal requirements are in place for appliances and devices, and minimum requirements for whatever's left for lighting. Those are really the only ones that are going to be applying to historic buildings in Oregon. In some other jurisdictions, it's going to be different, but that's going to be the case in Oregon.
Okay, and the other question we got, do the optimum start controls take into account the outdoor temperature to determine how long it will take to get the space to the desired temperature?
So the optimum start requirements are a little bit vague in the code. That definition that I gave you is really the entire definition. So within that definition, yes, you can take into account outdoor temperature, and a good optimum start system will consider not just, you know, how long has this system generally taken to get up to temperature. You know, it took 15 minutes yesterday doesn't mean it's going to take 15 minutes today. So that's a really basic one, is how long did it take yesterday and the day before and the day before, and I'm just going to average them all together. But a better piece of equipment control will actually take into account outdoor temperature and either increase or decrease its optimum start time. So the code does not require that your equipment have that more sophisticated optimum start control, but you certainly can use equipment that has that more sophisticated optimum start control.
Okay, that was the end of the questions.
All right, well, thank you everyone for joining us today. We actually finished on time. Sorry, we had to go a little bit fast to do it. And we weren't quite able to cover everything that's in the HVAC chapter, but this should give you a good overview of what's in the ASHRAE HVAC section. Please join us tomorrow. We'll be talking, we have 2 more webinars to talk about envelope and lighting. And if you should be receiving that follow-up email that Connie mentioned before with some of this information. And if you think of another question today that you didn't quite get to, then we'll try to get to those as well.